Hi, and welcome to Module 14 of Lecture 1. In this module, we're going to take a little step back from what we've been working on to go over a little bit some foundations of linear algebra, in particular the concept of scalars and vectors. Now I'm going to skip to the end of this slide to discuss why we're doing this before I start doing it. And the reason is this bottom thing right here, which is utility in statistics. It's going to turn out that all the data that we're going to use in our hypothesis tests, our independent and dependent variables, are going to be saved and recorded in the form of vectors. So it's helpful to understand up front what a vector looks like and what it can do, so that when you later see these things in the form of vectors, they're clear and not confusing to you. And that's really it. So again, all you should get out of this particular module is some additional familiarity with what a vector is, what it looks like. So when you see it later, it's not surprising. That's it. If you want to go on further and learn more about this topic, there's an entire series of video lectures that we use for Math Camp here at Duke that are also on this YouTube channel, and all the stuff about linear algebra and scalars and vectors and so on and much more are all in Lecture 10 in that video series, in that video course. That said, we'll start here and go through it pretty quickly. So the difference between a scalar and a vector is a scalar is just a number like you've seen before. So I'm going to use a C here to correspond to a scalar. In contrast, a vector, which I'm going to write as A with a little arrow over it, is just a list of scalars. So we often write it like this, with a little circle and a1, a2, and then if we have a longer vector, we can write a dot, 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 indicating an ellipse, indicating that it keeps going, and it ends at some a sub n. So it's an a with a subscript next to it. The subscript corresponds to the element in the vector. So the a1 is the first element, a2 is the second element, and so on down to the nth element, an. We can write vectors in different ways. As I said, an a with a little half arrow over it is a way of writing a vector. If I was using boldface in a text that I'm not writing by hand, that would also be a way of writing a vector. This is known as a column vector because in a column. You can also write a row vector, which is the same thing, just in a row. Sorry, sometimes if I push the wrong button, it waits forever. Okay, a row vector looks like this. And you can just space the things if you want, or you can put commas if you want. There's a row vector. The third way you can write a vector is graphically. So let's say I have a two-dimensional vector, and let's say my A is actually just like, let's say it's 1, 2 in 2 dimensions. Well, I can make a two-dimensional plane here, and I can say, okay, if this is 1 and this is 2, then the vector A is the arrow that takes 0 over to 1, 2 with a little arrow at the end of it, and that's a vector. So this is a graphical way of writing a vector. In all cases, all it really is a list of numbers, a list of scalars. And the reason, again, it's useful is that we're going to use this to store our data. What does that mean? Well, we might have our independent variable, x, and it would be a vector. And for every data point, we would have an element of x, x1, x2, and so on, down to the number of data points we have for x. And then you might have our dependent variable, y. And this is going to be y1, y2, and then all the way down to yn. So these two vectors store our data. The first one stores our independent variable data, and the second one stores our dependent variable data. And every subscript of 1 means it's the first data point. So if you're doing a survey, for instance, of 1,000 people, it will be the survey answers of that first person. Y here is the dependent variable, and x here is the independent explanatory variable. And x1 is the first person's value on that independent variable, and y1 is the first person's value on that dependent variable, and so on down to all n people in your survey pool, in your sample. Okay, so that's why we're going to care about this, because it's going to be very useful for storing these variables. And if you go on to use statistical tools like programs like R or Stata or other tools that you can use to do statistical analysis, or Python or anything else you end up using as part of data science applications, you're going to store your data as vectors or matrices, which are just vectors put together, as we'll discuss later. Okay. So that's why we care. That's why we use these at the moment. So we can do a few things with them that can be convenient. So I'm going to go through those now before finishing this up. So vector addition is pretty straightforward. As long as two vectors have the same length, and they must have the same length, then you can add two vectors by adding each individual element. So this vector a plus b is a1 plus b1 in the first element, and a2 plus b2 in the second element, all the way down to plus bn in the last element. Sorry, I'm using a pen poorly here while trying to look at the camera. So this is the way to add vectors. You can subtract in the same fashion. As long as the vectors are the same length, you can add them or subtract them just fine, and you do it element by element, and that's it. Scalar multiplication works the same way. You take some scalar, some constant c, multiply it by vector a, and you multiply it element by element. So the first element is ca1, and then ca2, and then all the way down to can. That's it. So scalar multiplication, like vector addition, is relatively straightforward once you know how to do it. You can also think about these things graphically. If I were to add a vector to this vector over here, I would take this like this, put the tail, call it, and the tip of the other vector together, and then draw a line from 0 to the tip of the other one, and that's the sum of those two vectors. For multiplication, I'll take the original vector and multiply it by number. So if I had a vector that looked like this, say 1, 1, I'll multiply it by 2, and I would get 2, 2. So this second vector would be twice as long as the first vector. This vector would be longer than the first vector because I'm multiplying each one by 2 to give me 2, 2. So it's longer than the previous vector, but in the same direction. So that's most of it, honestly. The very last thing we're going to talk about is how to multiply vectors together. And that turns out to be tricky. There are actually many ways to multiply vectors. Almost none of them we use in political science or statistics, except for the dot product, also called the scalar product. It's called the dot product because we write it by using dots. So a times b, with a dot in the middle, is a dot product. And that's called a scalar product because this product will equal some scalar c. So when you multiply two vectors together with a dot product or a scalar product, you get a scalar, a single number. Now to do this is actually not so bad. To calculate this, you take the first element of A, multiply it by the first element of B to get A1 times B1, and then you add it to the same thing for the second element. And so on, going down all the elements until you get to the nth element, which is also multiplied, and that thing will equal some constant, because all you're doing is multiplying constants, scalars, together over and over and over again to get a single outcome. I keep saying constant, but what I mean is scalar. I mean a single number, not a constant. These things can be variables too. So my apologies there. Okay, so that's a dot product. That's useful because the dot product tells us the angle between two vectors. Because another way of running a dot product, at least in sort of the two dimensions here, is that the dot product is the length of A times the length of B times the angle between them. So if the angle is 90 degrees, you get a cosine of 0, if you remember your trig. And that says the two vectors are perpendicular to each other. So there's no overlap, they're perpendicular. Whereas if the angle is 0, so exactly in line with each other, then the the dot product is just the multiplication of both the length of the two vectors. And the angle, again, if you draw the two vectors out, would be the angle between them. So if this is vector A and this is vector B, this is the theta we're talking about. So if it's 90 degrees, they're perpendicular, and if it's 0 degrees, they're on the same direction. And that's it. That's all we need to know right now about vectors and scalars. There's a lot more, as I said. If you want to go to look at the math camp, there's a ton of stuff that you can learn, and then beyond that as well. But for now, this will be sufficient to get a sense of what we'll be working with.